Hello, everyone. Thank you. Thank you all for joining us for the Canadian Underground Infrastructure Innovation Center Academy webinar titled AI and Information Engineering in Tunneling. Organized by the Canadian Underground Infrastructure Innovation Center, the University of Alberta, and Benjamin Media, the CUIIC Academy offers classes, courses, webinars, and events to help further underground infrastructure educational opportunities across Canada. The CUIIC Academy webinars happen every third Thursday of the month, and please join us for the next installment on October 16th, 2025. For a full list of upcoming and past webinars, please visit cuiic.ca for more information. Also, registration will open soon for the CUIIC Spring Summit between March 3rd and 5th, 2026 in Mississauga, Ontario. Visit cuiic.ca for more information. A special thank you for our 2025 webinar series sponsor, Ackerman. Thank you for supporting underground infrastructure and education and innovation. We'll now introduce today's speaker. Professor Mike Mooney is the Bruce E. Grewcock Chair Professor of Underground Construction and Tunneling at Colorado School of Mines. He is a member of the faculties of Civil Engineering and Mechanical Engineering, where he directs the Research Center for Underground, as well as postgraduate degree programs in underground construction and tunnel engineering. Mike received his bachelor's in physics, a master in structural engineering, and a PhD in geotechnical engineering. Mike teaches a number of different subjects and pursues research in pressure balance TBM tunneling, large diameter liner behavior, AI and the digital underground, and prediction/control of ground and building deformation. Mike was elected to the U.S. National Academy of Construction in 2024, and he is a registered professional engineer and a consultant on numerous tunneling projects in the U.S. and internationally. I will now pass it on to you, Professor Mooney.
Thank you, Raffaele. Let me just share my screen. Thank you all for joining. It's my pleasure to be here. I'm going to talk about AI and information engineering more broadly in tunneling. And information engineering is loosely here defined as the exploitation of data to advance tunnel construction practice here. Of course, it could be design as well. I am at Colorado School of Mines, and the work that you'll see here has been done by a big group of great students and postdocs that I've had the pleasure to work with over the past 5 to 10 years. So we all probably know about the forgetting curve. If you don't, this is memory retention as a function of time. And so you're with me for the hour. And so even after 20 minutes, you forget 40% of what you hear. And so I'm mindful of that. Now we can retain more information on this right-hand side plot if we remind you or participants, or if we are reminded of the points. And so I'm just going to give you my takeaways right away as a way to remind you. So number one, and I'll talk about this, of course, we've shown in our research that I'll describe here, that we can reduce TBM tunnel construction costs by 40% and reduce risk by 50% today with information engineering, the AI I will show today. Number two, these percentages can grow, of course, with development, with a cultural shift. Number three, we do need better sensing. We have lots of sensing on projects, but we need better sensing. And number four, tunnel construction really needs a cultural shift towards data-driven operations. Okay, so let's first start with the current state of data in tunnel construction. Tunnel design has come a long way, riding the wave of sensing technologies, computing, IT, and the Internet of Things. And so the state of practice today includes 3D digital geotechnical information and ground models, as you see in these two animations here. We have real-time ground and building deformation monitoring now is fairly standard practice on any tunnel project or underground project in an urban environment, as you see here with the City Rail Link in Auckland. And we have real-time sort of visualization where you can intuitively see how the movement of infrastructure occurs during the tunnel construction process. This is one example of one we developed here for the Queens Board tunnel projects, 4 tunnels in Queens, New York. TBM data, when dealing with tunnel boring machine projects, TBMs are outfitted with hundreds to thousands of sensors, and all that data is being provided every 1, 2, 5, 10 seconds, and is now harvested and can be used to learn from. And so we really have this real-time construction process monitoring capabilities via data. Lastly, then, all of this data is now integrated and provided in real time by various softwares, 2 of which you see here, but there are many others that really integrate all of this data and provide it to project stakeholders practically in real time. So lots of data at our fingertips. The question is it the right data? Is it sufficient? And are we getting the most from it? And that's really the topic of today, is getting the most from the data or moving in that direction. I think whenever we're dealing with data in any industry, we have to ask the question, answer the question, what problem are we trying to overcome here with AI and information engineering? And I think it's good to give an example from outside of underground to convey this. Let's use autonomous vehicles as an example. Autonomous vehicles use extensive sensing and extensive AI to enable their capabilities. What are they trying to overcome? Well, the motivation is shown here. There are 6.5 million accidents and 40,000 deaths per year in the US. Sorry, I didn't do look up the Canadian data, but for this, the average commute time is 60 minutes per day, and congestion is up to 150 delay hours per year, depending on where you live, which city you live in. So the potential benefits of autonomous vehicles or advancing those with AI and information engineering is a 100 times to 1,000 times reduction in accidents and deaths. That alone tells us this is worth pursuing. We can regain commute time for work or other activities if you don't have to be actively driving the vehicle. And many traffic or transportation agencies are relying on connected vehicles and AI to really improve efficiency and solve traffic congestion, which reduces that congestion that we all suffer through as drivers. So now coming back to underground, what problems are we trying to overcome with AI, with information engineering? I'll point to 2. One is risk, and specifically geotechnical risk, so that we all understand that in underground projects, we are essentially operating with majority uncertain conditions rather than unknown versus known. There's less than 0.1% of the ground is characterized using traditional site investigation. And so this leads to high uncertainty in geological and geotechnical conditions due to limited sampling. So these are just some examples of cross-sections that you will typically see on tunnel construction projects. This is the ground conditions in Seattle, where the different colors are different soil types. If you look carefully at these layers between different soil groups, you see question marks. So it's not clear where those boundaries lie. It's very difficult to estimate where those boundaries lie when you look at a borehole on the left-hand side here and a borehole on the right. But understanding where that boundary is, or more importantly, what is the uncertainty in where that boundary is really quite important to tunnel construction. We all know, if you have geotechnical background, that even within so-called homogeneous soil groups, the ground properties are stochastic. They really are not deterministic. They have means and variances that have to be characterized. And that brings a level of uncertainty into how the ground will behave and how construction will progress. So looking to the future, how do we get from 0.1% to 100% subsurface certainty? Well, sampling at 10%, let alone 100%, seems unreachable. it's cost prohibitive with today's techniques. So we have to think differently about how we gain this level of certainty and reduce that geotechnical risk. I'll offer that AI and machine learning certainly looks promising. Here's one example from my colleague in computer vision, where there's an original image here, and this image is sampled at 0.1%, quite like geotech. And then here is a reconstructed image from the sample data using computer vision technology. And so that looks quite a lot like the original. Now, this is a little bit stacked in favor of reconstruction because there's a definite pattern to this image. But nevertheless, the point of this is that with very sparse data and these more advanced techniques, there is opportunity to improve certainty. So we should be looking to take this approach in the underground industry. The second problem really is cost. And I'll point here to the boring company effect, which I'll just say is that otherwise known as everybody wants to build underground at a cost of $30 million per mile. Every community in the country, in the US anyway, and I'm sure Canada, raises their hand to say, yes, please build underground if you can build at $30 million per mile. But the actual costs are much higher than that. And that's a big problem in this industry. So if you look at, say, the efficiency statistics across different industries, this plot here just shows kind of gross added value as a function over the last 70 years or so, different industries. And you can see that the construction industry really hasn't gained in terms of productivity and efficiency. And so can AI, can information engineering improve upon efficiencies and drive down the cost of construction? So all that is to say, in this work, in this discussion today, I'm going to talk about optimizing tunnel boring machine performance and squeezing new information from TBM data with the goal of reducing risk and reducing cost. So I'm going to give a few different examples of work that we've done. The first is TBM optimization using machine learning. The benefits to be gained by optimizing TBM operational parameters include the following as examples. We can maximize the advance rate of the machine, can minimize cutter head torque, power consumption. We can minimize consumables such as soil conditioning costs and minimize tool wear on the machine. Some important notes here is that the relationships between TBM parameters and advance rate are really not known. There are no physics or mechanics-based formula in pressure balance tunneling in soft ground that predict this. And that's because there's a complicated nature to the excavation chamber versus what's happening at the cutter head. Also, the relationship between cutter head torque and TBM parameters does exist, but is often inaccurate, as I'll demonstrate. Soil conditioning, as you see in this video here, where we inject conditioning agents to soften the ground or to introduce a behavior that helps it be excavated from the ground more efficiently. That process is very much a black box. And then lastly, we cannot see the ground. There's the operators of a TBM, and they're looking at computer screens rather than looking at the ground. And so can we use techniques to improve in all of these areas? The first example I'll present is regarding cutter head torque. So early on in a slurry TBM project, we observed that the cutter head torque was considerably higher than what our mechanics-based models suggest it should be. So if we look over here, we see cutter head torque as a function of the advance number. You can see here it's roughly 800 ring advances along a project. The theoretical torque is what it should have been, is shown in this green dashed line, but the black data shows that very often it's much higher than that. And similarly down here in the bottom, it shows basically the same thing. And so we thought if the physics doesn't demonstrate or doesn't explain why the torque is high, then can we use machine learning to learn why the torque is high and to provide some insights into where is the model wrong and where is the physics-based model, not applicable. So we use machine learning. So as background, what is machine learning? algorithms that learn patterns from data with the goal to be descriptive, which is explaining what is happening or what has happened, or predictive, to predict what will happen in the future, or prescriptive, which is to make suggestions about what actions to take. And we really work with all three objectives. We first want to characterize why is the behavior the way it is, but we also want to be prescriptive so that we can actually develop algorithms that help projects become more efficient and TBMs operate more efficiently. I do like to poke fun a little bit at AI. AI is trotted out to be the be-all, end-all, but in some ways it's just relabeling statistics. Okay, so with machine learning, cutterhead torque modeling, the way we did this is we take samples each ring and we train a model. We use a significant percentage of the data that the TBM has collected during excavation, in this case 80%, randomly selected full rings. We leave 20% of those rings out, again, randomly selected, and those are used for validation of the model. And so what you see down here is assume a model now is developed where the model determines which parameters are important and produces essentially a prediction of what that torque will be. What you see here then in this middle plot is the essentially performance of the model on the validation data sets. So these gold rings that are entirely left out of model training. And you can see here the predicted torque is in red, black is measured, and the model does a good job of estimating what the cutterhead torque is along these this stretch of modeling. And then we test the model over 140 rings in this particular case, moving forward, none of which were used in training or validation. And you can see here that the model sometimes performs well, but oftentimes doesn't perform well, say, for example, here. And the reason for that is usually because the model is, or the TBM is encountering different ground or operating with different conditions. So one of the key things we do with the modeling or machine learning is capable of is teaching us what the key performance indicators are. So we learn which model parameters most influence the cutterhead torque. And so you can see here the cutterhead thrust force is the most important parameter, followed by penetration rate, excavation chamber pressure, and you can see some others below. Here, cutterhead thrust force is not total thrust force. That is a pertinent parameter for open mode tunneling or main beam rock machines. But with pressure balanced TBMs, you really have to look at the cutterhead thrust force alone, which is the force between essentially the average force across that face. Now, we can also look at specific contributions of these parameters to cutterhead torque, from which we can identify these KPI ranges that we can recommend and an operator of a TBM can use to optimize the machine. So here you see a plot of the contribution of this cutterhead thrust force to torque. And you can see here that essentially when you push hard, the torque goes up. This is somewhat intuitive. If you've ever taken a drill gun in the garage and drilled through wood, we know that if you push harder, then the cutterhead torque or the drill torque is going to go up. Oftentimes, there'll be a point beyond which that torque comes down. But in this case, you can see here, if the goal is to minimize torque, then the cutterhead thrust force really should be kept lower. Right, so there's an optimal range if the goal is simply to optimize, to keep the power consumption down. Another example here is the feed density. So this is a slurry TBM, and so the feed density, as the feed density increases, the cutterhead torque increases. You see by comparing these two, the relative influence, they're on the same scale. And so you can see here that ideally you want to keep the feed density on this particular case below this number. Not a huge penalty as long as the feed density stays below a much more reasonable number, which would be around 1.2. So from this, then, one can extract recommended ranges to minimize cutter head torque. And you can see an example of those. And the model then shows that the recommended ranges would lead to an average torque reduction of 40% compared to what the data was trained on. That's key. What are you comparing to? So 40% reduction if those KPIs would be achieved. Just looking a little bit further here, this just shows essentially the capabilities of machine learning. Here again is the measured and predicted cutter head torque. And you take a case where the cutter head torque goes quite high, and the machine learning model can help teach us why is it so high in this particular location. So you can see from this graph over here that the reason why the cutter head torque is really high in this location is because that cutter head thrust force is just really high. The operators are pushing very hard on the ground, and that's causing that torque to increase. Conversely, if we take a low area of torque and look at the model, you can see here that in this particular case, the cutter head thrust force was quite low, and then some other parameters that you can see here. And so these dashboard type features are really useful and easy to pull from the machine learning analysis. And then we can use these models, which are really, machine learning is in some ways black box in that you can't really, doesn't really tell you why until you start probing the model. And we can do that to explain why torque is high or why torque is low. And so this essentially is a very complex plot that shows two ring examples. Here's an example where the cutter head torque was low, ring 1858. Here's an example where cutter head torque was very high. And you can see here why. The reasons why torque was low, they weren't pushing as hard. I should also mention that the ground, of course, matters. And so the key parameter here was the fines content that's in the ground. And then in cases where the torque was really high, you can see here that the cutter head force was quite high. It was a more finer grained material compared to the earlier ring with low torque, etc. Okay, now switching over to advanced rate modeling. We do the same and have done the same process for estimating advance rate and trying to understand how do we optimize advance rate. And so similar machine learning approach was used to characterize the advance rate. And here you can see the parameters that are most important. We include cutter head torque in the model, but we note here that it's not a controllable parameter. So not terribly useful to an operator of a TBM. But besides that, the most important parameter, again, is the cutter head thrust force. And then you can see chamber pressure, rotation speed, and then some of the slurry parameters there. Similar to torque, these are contribution plots. And when you look at the contribution of the cutter head thrust force to the advance rate, you can see here that low cutter head thrust force actually allows the TBM to move faster with a higher advance rate. Very high cutter head thrust force actually slows down the TBM. And you see that in the data. And so from this, you can see an optimal range would be in this range, where you can see that the cutter head thrust force is somewhere between 2 and 3, let's say. The other parameters that are shown here, of course, if the rotation speed increases, typically a TBM is going to move faster because the penetration rate is generally constant. And then you can see the other parameters, the feed flow. As the feed flow increases, then you have a more diluted, let's say a lower solids concentration in the excavation chamber. It just behaves better. Same with the feed density, keeping that low. So recommended KPIs to maximize the advance rate. In this particular example, don't take these to the bank for every situation, can be determined along a project. And they can change, of course, as the ground changes. And so here the model shows, again, that if the KPI ranges are followed, then this would lead to an average advance rate increase of 35% compared to what this project was achieving during model checking. We can also then jointly optimize cutter head torque and advance rate. So if you want to both maximize the productivity of the machine, but also minimize energy consumption. That approach can be done, and that would then lead to a set of optimal parameters that you see up here for TBM operation. So these parameters can be then fed to operators and personnel on the project, and they can implement then, and then you can see right away if the model was correct, because you tell if the performance is improving. So what's the impact of this approach? Well, economic benefit for sure. Here's an example where prior to optimization, the contractor was doing what they feel is best. And these are 2 months, just 2 months prior to the implementation of KPIs. You can see here that the TBM parameters were majority outside of the recommended range, and only 4% of the time was the TBM being operated, we'll call it optimally. And then during the 2 months after the KPI model training and KPIs being fed to the project team, you can see that they're still majority of the time not operating in the recommended range, but certainly they went from 4% to 30% in terms of optimal. And the benefit of that is you can see over here, the advance rate increased here 12% from before using KPIs to after using KPIs in terms of advance rate. I'll mention again that had they been using this 100% of the time, that would have jumped to close to 40% improvement. And then cutter head torque reduced 25% prior to and after the introduction of the KPIs. And also it could have benefited 40%. The reason why the full 40% benefit was not reached, both in terms of advance rate and torque, is because the operators were not operating the machine in using the recommended ranges. Okay, so just moving on now, there's lots of processes on tunnel boring machines that are challenging and can benefit from just information engineering. And so soil conditioning is another one of those. I mentioned earlier that soil conditioning is the injection of foams and polymers, whether in foam form or in liquid form, and mixing with the ground and then ingesting that material. Well, this is part art, part science. Lab testing is helpful, but ultimately the appropriate conditioning strategy depends on the TBM configuration and the TBM ground interaction. So it's really important to learn as you go, and that's where information engineering is quite valuable. And so just one example here where we learned about what is the benefit of the injection of foam to cutter head torque and to advance rate, because those are two areas where a foam injection will influence performance. And so you can disregard all the details here, but the key thing here is one of the parameters when you're in auto and semi-auto mode operation is the foam injection ratio. And what you see here is that the foam injection, as the foam injection is increased, the cutter head torque decreases, and that's intuitive. But there's a certain foam injection rate beyond which there is no benefit in terms of cutter head torque. Similarly, with the advance rate, here you see versus foam rate, and it's very similar. This is foam injection rate. There is a benefit to the advance rate as you inject foam. The machine, the TBM, is able to move faster because it softens the material, is able to process it better. But there is a upper limit beyond which there's really no benefit. And so this is very helpful in determining where that limit is, because beyond that, you can argue, the data shows that the contractor is just wasting money by injecting these materials. Another aspect is predicting tool wear. We all understand that tool wear is quite important on TBMs, particularly pressure balanced TBMs, where it's very expensive to just go out and inspect the tools. And so trying to understand what the wear on the tools are all the time is really valuable. And it is intuitive that the machine will behave differently as the tools wear down. And this comes through in the data. This is one example of where we just look at this parameter, which is the cutter head torque, normalized by the penetration rate and the cutter head thrust force, and we plot that versus the average wear. And so here's two clusters of data where we can see here that the red data is with brand new disc cutters on a soft ground machine, and then the blue is with disc cutters that had average wear of 10 millimeters. And so there's a notable difference in this parameter that then can be used to infer what a tool wear is. And then lastly, with a soft ground machines, cutter head clogging is a significant risk and oftentimes difficult to determine when the onset of is occurring. And so this is a case where we were able to clearly show, based on the TBM parameters, that the cutter head clogging reveals itself in the performance data of the machine. Okay, moving on then to one additional area, perhaps the last here area for today's talk, is machine learning-based ground characterization. So pressure balanced TBMs, whether they're earth pressure balanced, slurry, or variable density, operators are advancing in the blind. They cannot view the face like in a main beam open mode machine. The as-encounter ground conditions are just not visible to them. So they really are relying on instrumentation. And in an earth pressure balanced machine, they might be able to go out and look at the conveyor belt to generally understand what kind of ground it is. But even on the belt, this is all mixed up from the face and covered with injected materials. So it's sometimes difficult visually to see what is there. So it is intuitive, though, that the TBM will tell us what the ground type is, or certainly tell us when the ground changes. And so here's an example where we used machine learning to characterize the as-encounter ground conditions. So here you see a project in Seattle. Again, the different colors are the different soil types. And this block here is essentially pulling from the tunnel alignment what the ground conditions were predicted to be in the geological cross-section in the GBR. And so what we did was we developed a machine learning algorithm that was trained on boring logs. And as the TBM traversed across the alignment, the machine learning algorithm predicted this ground condition. And you can see here that it matches pretty well. It's able to characterize what the ground conditions are, at least comparable to the geotechnical baseline report there. The methodology used for this is a semi-supervised learning. Semi-supervised means supervised learning is the process where you have factual data, you know the ground truth, and we really only know the ground truth at the borehole locations. So you can imagine as the tunnel boring machine passes a location of a borehole, then we can use that as a supervised learning example. And there's 100 boreholes or hundreds of boreholes, and every time it passes one of those boreholes, that provides the data for supervised learning. But everywhere else, we use unsupervised learning. And so we're really just using a similarity graph approach to combined with the supervised learning piece to develop the algorithm. There's more, there's a reference here for those interested further. And so to demonstrate the method correctly, because we saw some differences between our prediction, which is on the bottom versus top, and usually it's at the fringes or the transitions between soil groups. And so in this particular case, we had a separate research project where we had installed vibration sensing on a tunnel boring machine to detect impacts with cobbles and boulders. And those cobbles and boulders occur in Seattle in the glacial till material. So all these black dots here are locations of known glacial till. And so we found from that analysis that our prediction was actually quite accurate because it showed more glacial till in our prediction in the zones where we knew those cobbles and boulders were being detected. Okay, so with that, I'm just going to now transition into a bit of a conclusion here. So some concluding thoughts here about information engineering and maybe particularly AI, machine learning. Of course, AI is now fully upon us all in our daily lives. And so it is impacting us now and will certainly impact us going forward. But if we think about underground, what does the future hold? That seems a bit of a fool's errand, as you can see in this meme here. Not mine, but something I found on the internet that conveys a funny observation. But if we look to the future in terms of what might AI bring to construction and engineering, architecture, et cetera. So this is an interesting analysis or prediction of what share of industry employment might be exposed to automation by AI, because the low-hanging fruit with AI is automation. And you can see there's quite a high percentage, 1/3 or more for architecture and engineering, but only 6% predicted for construction and extraction, which is quite a low expectation that hopefully will not come to fruition and will be, I presume, more than that 6% in practice. There's certainly, I've talked all today about large language models, the chatbots. That's what's really dominating, I think, our everyday lives. But there's significant impact of large language models. A couple of funnies from that apply to the education world is essentially here, where as our college professors, it really changes the way we have to teach, as you can see here on the left-hand side, the use of chatbots. And now if we say that only handwritten work is accepted now because of AI, then this is what we get from that, is a nice automation of page turning and writing as if it was done by hand. Okay, so just thoughts to leave you with, just like I started with. I've shown today that really information engineering, which includes AI, certainly can reduce construction cost and can reduce risk. These numbers, 40% and 50%, were just taken from the examples I gave. But whether those numbers are half of that, I would argue that's still a significant improvement on these billion-dollar infrastructure projects. Those percentages will grow for sure. We do need better sensing. For example, with tunnel boring machines, we have very little sensing in the most important location, which is at the cutter head. And then lastly, I just argue that tunnel construction, in order to really be driven by data, tunnel construction needs a cultural shift towards data-driven operations. We're starting to see that, but we're not there yet. And so I think the companies that really embrace this and make decisions during operations based on a data-driven approach, I think will reap the benefits from that. And again, just finally, to make a little bit of fun at machine learning, it also often predicts obvious things. And so like with anything, you have to be careful with the use of machine learning. Lastly, I would just invite you all to attend the Tunneling Fundamentals Practice and Innovation short course here at Colorado School of Mines. It is in October, so it's nearly 1 month from now. You can learn more there's lots of hands-on labs. There's in-class material and then hands-on labs every afternoon. There's a detailed program at this URL below, or you can just Google Colorado School of Mines Tunneling short course. And I remind you today in particular, because the early bird registration ends tomorrow. It says September 16, which is not tomorrow. It's September 19, which is tomorrow. And with that, I thank you for listening.
Well, thank you very much, Professor Mooney, for this truly inspiring presentation. Certainly learned a lot. I want to remind everyone that please, if you have any question, please you can submit them so we can address them right now. I have a couple questions that I would like to start with. So we have discussed a lot of applications of these methodologies, and I just wanted to ask you, what are the most frequent practical applications of this approach? Are they more often applied during the course of a project? For example, learning at the early stage of tunneling and then application and implementation in the later stage of tunneling, or is there also some application that is prior to a project during the design phase?
Yeah, I think, Raffaele, both. I didn't at all really cover the use of AI in the planning and the design phase, but that's really a separate conversation. But in my just review of what some people are doing and some work we're doing here, there's a lot of ability to do sort of AI application to, let's call it white collar work, right? Programming work and automating processes that look at different alignments, using large language models to explore for data in data repositories. So I think in reality, while I focus today on the construction side of things, I would say there's been much more actual implementation of AI, particularly with large language models in sort of the pre-construction design and planning phases.
Very, very well. Thank you for that. We have a couple questions. Mostly we have appreciation and thanks for this presentation. It was very well received. One question from Christopher Lamont. How do you see AI learning being, or can it be, applied to the slurry-based methods? You have talked a lot probably about EPB, but any application to the slurry-based methods?
Yeah, I mean, the whole torque example I gave to start the presentation was on a slurry TBM. And so AI is we found it to be quite, machine learning, I will say, we found it to be quite useful in slurry TBM projects. So we've done that on multiple slurry TBM projects now, as well as multiple EPB projects. And we find it has great potential and benefit in both.
Thank you. I have a couple more questions. I'm sorry to steal all this time, but so you spoke about our sensing capability, and we need to improve our sensing capability. What is the importance, and probably that's a rhetorical question, but what is the importance of the quality of the sensor, the type of sensor, the placement of the sensor, and is anything that is being now with all this learning that we are having now, is there anything that is being prescribed for a contractor prior to the start of a project or during contractual arrangements, like anything that is prescribed for permitting this learning and these innovations?
Yeah, well, I'll just start with, we all understand the expression garbage in, garbage out, right? And if you don't have good data, then whatever you come up with, whatever algorithm you're using is going to give you the wrong answer if your input's no good. So we all understand the importance of the data, and the more rich the data, the more benefit anyone will all get with this. We have found with tunnel boring machine projects that there is lots of sensors on TBMs, but there's also high error rates in sensor data. And I think that's maybe, if we look back a decade ago compared to today, or even 15 years ago, we're living through this generation of get as much data as possible, get as many sensors on TBMs, and just get data. And I think now we're moving into that phase where, hey, let's make sure that this data is accurate. And let's make sure that the sensors are placed in locations and measuring the things that are useful on projects. And so I think we're in this very, very important phase, the industry is, of making sure these sensors are providing data that's correct. It's a challenge when you think about tunnel boring machines, when you think about, for example, excavation chamber pressure sensors or flow meters, making sure in these rough environments that these sensors are providing correct data and recalibrating on a frequent basis. It's a big effort to do that, but it's vitally important for these data-driven methods.
Thank you very much. We have another question in from AJ Daras. How do you decide if a problem is suitable for AI and machine learning? What kind of things do you look for making that decision?
That's a good question. So we have started with problems that are not well defined by mechanics and physics. Maybe I'm a bit old school here, but engineers are trained in mechanics and physics, and if we understand the physics of something, then we use physics to explore processes. And so really the first criteria for us is if it's not defined by physics or mechanics very well, then we try to apply a data-driven approach. And the data-driven approach, I should mention that the data-driven approach is a great way to kind of reverse engineer something, to learn what the physics is and bring it back to a mechanics understanding. Because we all know that, all this stuff is driven by physics and the laws of gravity, et cetera. So we just don't know them exactly how it's behaving. So it's important for us anyway, and my message would be, it's important to always be pivoting back to the roots, which is mechanics. So there's that. The second thing is you got to have data, right? These machine learning based approaches, they're data-driven approaches. If you don't have data, you can't learn extensively. And so a good example of that is when I described that ground characterization. If we strictly use borehole data, you have a borehole every 50 to 100 meters, and a borehole being 10 centimeters in diameter. That's not a lot of data to apply to a full project. So we have to supplement that with what I called unsupervised learning. So you've got to have data in order to make machine learning techniques work. And that's why these large language models have been so successful, is because they're harvesting everything that's on the internet.
Thank you very much. We have a few more questions. This one is from Inching Park. Thank you, Professor Mooney, for an informative presentation. According to your slides, optimized KPIs recommendations are obtained from the previous data. At the beginning of the tunneling, such information might not be readily available. At which stage such information can be sufficiently obtained and be provided to the tunneling contractors? And this question may overlap with the previous question, but it's a very good question.
Yeah, that's a great question. And so it's a good point. You don't know what to do until you get data. And so if a TBM begins excavating and it's moving through material one, let's call it, and it's going to transition into a new material where that will impact the interaction of the machine with the ground and change the behavior, you can't make predictions about that material two until you've introduced that data into the model. And so when you go into a project, you have to train a model, and the distance over which a robust training occurs really depends on the project. If you're going like in Seattle, for example, where you have a high variability in lots of different materials, you can train a model fairly quickly if you're moving in and out of different materials. But conversely, if you have a very simple stratigraphy where maybe you transition from material one to material two, and I'm being quite simple with these, as soon as the TBM transitions into that second material, then the model from the first part is not reliable for that second material because, of course, the ground matters. The model requires retraining. So one thing I didn't really talk about is when implementing this on projects in practice, you have to continually be checking to see, is the model still accurate? Is it still accurate? And if it's not, then you're retraining. And that helps you understand whether you're relying on a model that's useful or a model that's not useful.
Very good. Thank you very much. Another question from Michael Lywood. Are owners incorporating an evaluation of contractors' AI models in contract awards?
I would say no. In North America, I've not seen that being implemented. Certainly in North America. I'm also involved in AI underground projects in Asia. And while owners are really pushing the adoption of AI, I haven't seen it as a contractual framework, in a contractual framework yet.
Thank you. I have another question. So the application of these methodologies are probably a cost-benefit. They come after a cost-benefit evaluation, right? They are not for free. You have sensors that you need to improve and you need to add to the machines. So are these applications more for selected high-value projects where the gain can be considerable and can justify this expense? And I say this having in mind other underground industries such as trenchless or microtunneling, for which probably I've not seen the same kind of attention. Is it because of the value of these contracts, the size of these projects, or is because of a different kind of technology that perhaps cannot be applied yet?
Yeah, I think, well, to certainly a cost-benefit analysis, stating what level of project would warrant this approach is difficult, right? Because we're in early days, I would say. But I would say any larger diameter mainstream tunnel boring machine project where you've got operational costs on the order of hundreds of thousands of US dollars per day, merits will find a cost benefit in favor of doing this. Because as I showed earlier, if you can get a 10% increase in, for example, advance rate, even a 5% increase in advance rate that enables you to install one extra ring per day per 24-hour cycle. So you're talking 20 rings per month. And if you start doing the math there, then you're able to shave off days to weeks on the entire tunnel project, and at burn rates or operational cost rates of $200,000 to $300,000 per day, then you're talking millions of dollars in savings, even from a small optimizational benefit, right? So I think there's that. That's how it should be, I think, evaluated. I think when it comes to trenchless projects, I think the industry will get there. One of the limitations I will say with trenchless with trenchless is data, right? So in a lot of, say, HDD operations, you don't have a lot of data to be able to build models from. But I do think that we're just in the early days of the application, and I'm sure there'll be some innovative approaches to developing for all kinds of project scales.
Thank you very much. That's very true. I think we're almost out of time. I don't see any additional questions. So I want to take advantage of this time to thank Professor Mooney for this presentation. It was really interesting and inspiring. I learned a lot today. And I want to thank the CUIIC members and the CUIIC Academy and all the audience that participated today, and all the audience that participated with questions. That was very, very, very helpful and very interesting. So if there is no other question, I think we are good to end today's session. Thank you, everyone.
Thanks.